Hello everyone, Rabi from RKALC. Today we're talking about pad footings in rock, landing on rock or landing on less competent subgrade. Um, we'll be using two applications, which is the pad footing under the concrete calculator, as well as the wall strut-and-tie, where the footing is having proportions of strut-and-tie. I mean, the span to depth ratio is less than 1.5 to section 12 of Australian standards. We'll be walking you through two different examples, the bendy one and the strut-and-tie one. First one is the bendy footing. Or the flexural footing, if we want to call it. The size of this footing is chosen as 2.1 by 1.5. That was um, driven by the bearing capacity. Here we are talking about 700 kPa shale. It can be 200, 250 if you are talking about sands, or probably less. But here we're talking about class 5 shale. That has resulted in the size of the footing being 1.4 by 2.1, and the span to depth ratio here is slightly above 1.5. Loads applied are 1,500 kilonewton for dead load, 400 for live load. So the ultimate is 1900 SLS and 2400 ULS. Now with the outstand checks, we just work out the effective depth. You can work to the depth itself, but I want to do here, make the ratio of the outstand divided by the depth. I use here the effective depth is becoming more than 1.5, and therefore we are on a flexural zone. If the footing is bigger or shallower comparing to its depth, then you will be comfortably more than 1.5. Flexural design, first things first, you just multiply the bearing pressure, multiplied by L squared, which is the outstand, divided by 2. And then that becomes 123. The minimum reinforcement is 798 to section 9 of the standard. And then AS required, you can use the simplified formula here, which is moment raised to the power 6 for the compatibility of units divided by 0.7 of Fy by the effective depth. That becomes 960 square millimeters. You can use then N16 at 200, which is 1001 millimeter square each way. So now that is for flexural, and then you go punching shear. You work out the critical shear parameter, which is at the D of face of the support. You work out that length and multiply by the depth. Then you get the area of that vertical plane. So you work out the stress. So you've got the loading applied onto the column divided by the critical shear parameter will give you the shear stress, and then you compare it with the allowance in the standard. But you have a concession. You can delete or take this out, this area, which is a direct bearing, out of the punching shear, and then use the remainder of the loading. This is what I've done here, which is pretty standard to get the section working as it should be. And then you work out the phi or phi FCV, which is the shear stress to Australian standard at section 933, and then you get your utilization. So there is no punching shear problem there. And you also will need to work out the one-way shear or the beam shear that is at D from the face of support. So you work out the center of the loading at that area there beyond the D, and then multiply by the vertical plane, so you get shear stress, and you compare it with the code allowance. Just note there that RKALC at the moment is still adopting 2009 standard, which gives slightly more conservative. Anyways, it doesn't make a big of a difference. And then you need to do also a column bearing check, i.e. the stress under the column. It has to be less than allowable stresses. You do the ratio of A2 divided by A1. A2 is the area after the stress dispersion to the area under the column. So that will give you like an enhancement factor. You multiply it by the allowable stress. So that is square root of A2 divided by A1, which is capped by 2. Then everything is fine there. And development of the reinforcement. This is a compression case, so the development will be circa 20, 25 diameters. Shouldn't be any problem there, especially that the column here doesn't require more than 16. Even if your columns are at 24 or 28, which is something might be dictated by um, um, buckling, but the section capacity itself would work there in 16. So that is a matter of judgment. You go then, you can mimic the same thing or apply the same numbers on the RKALC calculator, which is under the column or under the concrete calculator on the sidebar, and then you get the same numbers. So this example serves as verification, numerical verification for the RKALC calculation. So that is the standard part of the pad footings, where you've got a flexural footing. And of course, you can, once you've calculated the footing under RKALC, you can generate a nice and neat calculation report and print it, add it to your calculation folder. The next one is where it's a bit more advanced there, where you've got a strut-and-tie proportion. So that is another footing. We've got 3,000 kPa, and the loading is 6,000 ultimate, which is broken down to 3750 and 1200 kilonewton. So you size up the footing to that. It becomes 1.1 times 1.8 is the size of the footing, and the SLS loading is 4950, so you get 2500 less than 3000, so that is all fine. I'd always recommend that you size up your footing to have a minimum of 400 outstand for the reinforcement of the column to cog nicely outside of the footing, as the builder might be expecting you to do. Although if I just go to the first page of this one, you can cog your reinforcement in this direction or in an angle or into the column if you are very, very keen to reduce your footing size. Now, going to what we have here, if the working out the span to depth ratio, you've got the outstand is 400 and the depth, effective depth is 615, so that is 0.65, so that is less, where they stand 1.5, so non-flexural member, and then you will be talking about nodes at the bottom, CCT nodes, and a CCC node at the top with the footing looking like that. We will need to use the strut-and-tie calculation module, the wall module that we've spoken about in a previous Learning Center video. But before that, you just need to look at the analogy. We will assume that the footing is sitting on notional two wide columns on this scenario, and then acting in between. So you've got the strut throwing the load that will be half of the column loading going to this half node down to this, and then it will be the reaction will be equivalent to half column loading there, and then the ratio or like projection of that strut onto the horizontal becomes the tie, which is the reinforcement. Now the depth of the node itself is dictated by where the reinforcement is going to be drawn or going to be located in reality. So you usually have like 50 or 60 millimeters cover at the bottom of the footings, depending on your durability conditions, and the footing will be one layer. So you work out where the center of the reinforcement is, and then that will be essentially the dictate the depth of the nodes. Now, the top node doesn't matter how shallow you make it or deep. It should be as shallow as possible, so you increase the lever arm between the top and the bottom, and therefore get less reinforcement. But again, you need to maintain an angle of 60 or 70 degrees tops for the strut-and-tie modeling to work properly to Schlick. Now, going again to the strut-and-tie model there, I'll just feed the same numbers that we've got. I'll take the width of the footing. Here is 1100, 1100, and the depth of the footing is 700, so that becomes 700, and the depth into the page is 1800, right? And then you put the width of applied load, which is the column there. Location will be in middle. It will update you the figure here in real time. Width of support will be 450 here, which is that distance there. You can't go beyond that. And then 330, 30. So that is your model there. And you feed the loading, which is 6300. And then you've got 4950. So you've got all of the calculations now generated. Everything is green, means that you're all pass with all of the nodes without any issues. Here is what we've got. So strut loading, by doing the node equilibrium, you get the strut loading 3359, and the tie load will be 1167, which is what we have there exactly on the figure by projecting. And you've got the angle of the strut at 69. If you are not happy with 69, you can, and the footing is 700, for example, you can reduce the calculation depth of the footing to work out the reinforcement will be more conservative. That's a matter of judgment by the engineers. Now, the software will give you all of the checks depending on where the node is. So you've got the top node is CCC. So you've got the beta factor is 1 there. So you multiply by 0.65, which is 5, for strut-and-tie to the 2018 standard, by beta factor by 0.9, reduction factor, and concrete strength. So that is the node capacity, which is the one that you see here. And if you've got CCT multiplied by beta of 0.8, so you got 18, which is the number that you see here. So all of the nodes are passed. Recognize there, if you've got the angle of the strut is not normal to that surface of the node, so you will get shear applied onto the node, which is going to be worked out through more circuits. So that is the maximum and the minimum stress in your node, essentially, and that will be the maximum shear applied into it. Now, going down again, so the next will be working out the struts. So you've got 2 scenarios for checking the struts. Now, just first things first, this is a fan-shaped strut. Strictly speaking, you don't need to do bursting calculation, but I will do it for the sake of it, just to see how the calculation is being made. So you've got 2 scenarios, ultimate and service. With the ultimate, you take the strut load, and then you have an angle of dispersion in the Australian standard that is 11.31. You can work it out by it's a cosine actually in the Australian standard, so it becomes at 11.31. So you take that load and then convert it to by projecting of the angles becomes 17.13, and then you again project it on this. So these two forces together are the bursting and the ultimate scenario, and you've got a steeper or bigger angle for serviceability against serviceability load, which is always governing the design for strut checking. If your loading or the strut or the bursting loading is more than the concrete capacity on bursting, then you'll need bursting reinforcement. Otherwise, you don't. In this scenario, we will need because like working on the limitations of the Australian standard, it will require it. So that is what we have here in this example. You can go through it in detail by reading the Learning Center page. And then the software will generate for you um, um, a calculation on the struts by clicking on this one. So it will give you all of those detailed numbers in relation to efficiency factor, strut force there, the one that we've seen on the other example, on this actually very example here. And then it works out the allowable MPa based on efficiency factor and the concrete, the tension capacity, and the critical bursting capacity, and now the loading that we've got on the bursting uh, until you go all the way down to the reinforcement required. Now, just note that this reinforcement is on total reinforcement on both faces. Look at the first example we've published on the Learning Center to learn about how you put the reinforcement into the struts. And once you're done, you just click on calculation. So you'll get the same stuff. I need to, first of all, activate all of that and then click on the calculation. So you'll get the calculation report for the whole thing. That is the one that you see at the end of this report. That is all about it, I would say. At the end of the day, the reinforcement will be looking like this. And then just one note that you need to make sure that your reinforcement is developed properly beyond the node. So this is a figure from the ACI, because there is no enough guidance on the Australian standard current one as to where the anchorage should be. So you have there is the node itself. So beyond the node, you need to go tension lab, and if reinforcement is cogged, which is the case of about pad footing, so you are permitted to reduce that length by half. So let's say you've got 50 times diameter. Um, so it will need, let's say, 1 meter, but if you cook it, it will be half a meter. But there is another enhancement that is the extended nodal zone, if you want to call it. So in this scenario, uh, on this figure, so the extended node zone, it's all from here all the way to there. So you shouldn't have a problem per se on anchorage for the reinforcement. And then you've got the calculation report, which is all what you need to document your project. Look at the RKALC Learning Center in the next few hours to see this published video. Thank you very much.